In this lesson, we're going to solve right triangle word problems. To help us get started, we're going to solve two right triangles without any context. So for this first example right here, find x and y. So you might want to go ahead and label what I have here on your triangle. So we're finding x and y. We're given the length of the hypotenuse, and we're also given one of the acute angles of 30 degrees. There's a couple ways that we can solve this. We can use our knowledge of special right triangles. Since I see a 30-degree angle, I know and remember about the 30, 60, 90 relationships. So just real quickly, 30, 60, 90. If I know the length of the short leg is x, then I know the length of the hypotenuse is double that. And then I also know if I have the short leg length of x, I would multiply that by square root of 3 to get the length of the long leg. So one way that we could solve this is by our knowledge of special right triangles because of that 30 degrees. So when I look at what I need to find the opposite side, and I need to find the adjacent side, and I'm given the hypotenuse of 15. So in the special right triangle, because I have the length of 15 underneath the 90-degree angle, I can actually cut it in half and get 7.5 for the length of y. So just by our knowledge of special right triangles, I can say that y, this leg length, is 7.5. To find the length of the long leg, which is across from the 60-degree angle, all I need to do is take y's value and multiply it by square root of 3, 7.5 times square root of 3. Okay, now this is a little bit tricky right here. You can see the presentation of this. I would probably put 7.5 in parentheses just to make sure we understand we're multiplying. Typically, we don't leave a product with a decimal and a radical. So I'm gonna go ahead and change 7.5, 7.5 to 15 halves. So if 7.5 is 15 halves, I'd take 15, multiply it by the square root of 3, and divide it by 2. So certainly, don't forget about your special right triangles. If you want to use that, that's fine. Another way is to use a trig ratio to find y and x. So a second method would be to set up an appropriate trig ratio that would allow us to find either x or y. So I guess let's say that I want to find y first using a different method. Okay, notice that we have a need for y, but we also have the hypotenuse. We have 30 degrees. We want to find the side across from it, opposite, but we have the hypotenuse. So opposite over hypotenuse is sine. So if I go and go, well, sine of 30 degrees is going to be equal to opposite y over 15. I could set up that trig ratio. Now to get y by itself, I can multiply both sides by 15. Another strategy mathematically is to put sine of 30 degrees over 1, do cross multiplication. Either way, you're going to get y equals 15 usually goes up front, 15 times sine of 30 degrees. If you don't remember what sine of 30 degrees is from the unit circle, which is a half, that's fine. You can just go to your calculator, make sure you're in degree mode. I am. And just do 15 times sine of 30. So we do end up getting 7.5. So that method confirms with the first method. All right, what if we wanted to find x, not using special right triangles because we forgot about the special right triangles? Well, all right, if I'm looking to find x, I know with regard to what I'm given, 30 degrees, I want to find the adjacent side, but the other side that I do have length is the hypotenuse. So adjacent over hypotenuse is cosine. So I'd go, okay, cosine of 30 degrees would equal the fraction x over 15, multiply both sides by 15, or again, you could do cross multiplication, but you're still going to get x equals 15 times cosine of 30 degrees. All right, of course, you can go straight to your calculator and find that decimal amount, but you might remember that cosine of 30 degrees from the unit circle, the x-coordinate at 30 degrees is square root of 3 over 2. I could just end up multiplying by square root of 3 over 2 instead of getting a decimal. So this is an exact answer right here. Otherwise, when you change it to a decimal, it's just an approximate. But whether we use the special right triangles knowledge or we used a trig ratio, we should end up with the same answer. All right, let's do another example without context. All right, so you might want to fill in the right triangle that you have in your paper. All right, we're going to label the hypotenuse R. We're going to label the side across from the smaller angle y. We're given the adjacent side to 30 Again, I can use my special right triangles. So I know this is 60 degrees. And so this would be the length of the long leg. If I wanted to divide by square root of 3, that would give me the length of the short leg, which would be 105 divided by square root of 3. I would double that and get the length of the hypotenuse. Otherwise, we can set up trig ratios. So I'm just going to go that route, trig ratio. I want to find y first. All right, so to find y, I know that's the opposite side, and I have information about the adjacent side. So what is opposite over adjacent? Well, that's the tangent ratio. And that'd be y over 105. Let's multiply both sides by 105. Put 105 up front. Okay, I know I can get the tangent of 30 degrees as exact value from the unit circle if I wanted to, but if I have the use of a calculator, I'm just going to go with that. I believe I was still in degree mode. We're round to 3 decimal places. All right. To get the length of r, which is the hypotenuse, again, I can use 30, 60, 90 relationships. I can actually double this value and get 121 something, and that would be the length of the hypotenuse. Otherwise, if I want to show the trig ratio, going back to what I'm given, I've got the 30-degree angle, I have the adjacent side, and then I want the hypotenuse. So adjacent hypotenuse is cosine. So cosine of 30 degrees would be equal to the fraction 105 over r. Now notice the variable is down here in the denominator. There are a couple of ways that we can approach this. We can like multiply, cross multiply this way. Or we can actually just flip both sides of this equation. So if I were to reciprocate, I'd get 1 over cosine of 30 degrees equals r over 105. Instead of cross multiplying, I think this is the easier way to get r out of the denominator, but don't forget to reciprocate the other side of the equation. Now, I guess I still have to do cross multiplication, don't I? I guess I probably should have just done it up here. R times cosine of 30, we would usually put the r up front. Excuse me, that's 30 degrees. Equals 105. Let's divide by cosine of 30 degrees on both sides of the equation. And let's go to our calculator. Remember, it should be about double that value because that's the length of the short leg. So anyway, 100, let's do that on the calculator. Yeah, that's what we predicted. Let's round to 3,244. There are no units that were given, so I'm not obligated to list any units on my answers. All right, we're going to solve some right triangle word problems, and I'm going to use my trig ratios. If you notice that the word problem involves a special right triangle, well, you can always use that as well. All right, you might want to take a moment and read through this problem right here, and then we'll draw a picture. All right, this surveyor is standing 50 feet along a horizontal line, a flat line, from the base of a tree. Like that. I would have failed art, remember? So the surveyor is standing 50 feet, go ahead and put the units on here, from the base of a large tree. The surveyor measures the angle of elevation to the top of the tree as 71.5 degrees. So from his eyesight, her eyesight, whatever, from the horizontal, from the flat line up to the tip of the tree, this angle in here is 71.5 degrees. The question is, how tall is the tree? All right, so we are dealing with right triangle trigonometry. Here's our right angle, 71.5 degrees. If I wanted to know what this angle measure was, I'd just find its complement, subtract from 90 degrees. Don't know that I need it. I'll label the height of the tree as h. So we got to find h. So thinking about what we have an angle, we have the adjacent side, and we want the opposite side. We have no need for the hypotenuse. So opposite over adjacent is tangent. So let's set up the trig ratio. Tangent of 71.5 degrees equals h over 50 feet. Because the variable's on top, I can just simply multiply both sides by 50. So the height of the tree is going to be the product of 50 tangent 71.5 degrees. Notice we couldn't use a special right triangle because 71.5 degrees is not one of those degree measures that make up those special right triangles. Oh, we'll round to 3 places. Do we need units on the answer? Yes. We'll put feet here. So we've got to figure out what trig ratio we're going to use to solve the right triangle word problem. Okay, go ahead and take a moment and read through this next example. Pause the video if you need to, and then we'll draw a picture. We'll let this be the river. Okay, we are 200 yards from the river. Straight line distance, we're 200 yards straight from the river. But instead of going straight to the river, we're going to actually walk along a path covering a distance of 400 yards until we get to the edge of the river. Let me make sure I've got it labeled right. You're 200 yards from a river. Rather than walking directly to the river, we're going to walk along a path that's 400 yards to get to the river's edge. Here's the right angle. Find the acute angle theta between this path and the river's edge. Between this path and the river's edge. So this is the angle we're finding. All right, so to find this angle, what do we have? Well, I don't have any of the angle measures, but according to this angle right here, this perspective, we have opposite and hypotenuse. So I'm thinking, okay, I've got this theta that I need to find. I've got its opposite side and its hypotenuse. Opposite over hypotenuse is sine. So that's going to be the trig ratio we have to use. Sine of theta equals 200 over 400. All right, at this point I might reduce. So sine of theta is actually equal to a half. Well, at this point, I don't even need to use my calculator. If I think about the unit circle, I recognize 1/2. 1/2 on the unit circle is at this angle measure right here. The y-coordinate is 1/2. And I know when the y-coordinate is 1/2, I'm at a 30-degree angle. So without doing any kind of work, I can use the knowledge of the unit circle to help me find theta. Theta has to be 30 degrees to get a sine of 1/2. Now, if you don't want to think about the unit circle, that's okay. We've already learned how to solve this analytically as well. If I want to find theta, we brought in the arc sine on both sides of the equation. To undo the sine, so we get theta equals arc sine of 1/2. So we strictly go to our calculator and find an answer. So I want my answer in degrees, so I want to make sure my mode is in degrees. It is. And then second sine of a half, I'll just put in 0.5 instead, and we do get 30 degrees. You can always check your work. What's the sine of 30 degrees? It will give you a half, which is what we have here. All right, continuing to solve right triangle word problems, go ahead and take a moment and read through the next example. And then we'll draw a picture. So this is a skateboard ramp. This is our right triangle. We'll call this C, the length of the skateboard ramp. Then it says, find the horizontal length A of the ramp. So that must mean this distance right here. So we'll call that A. I think there's some missing information. This must have come from the textbook. So let me look at my notes here. Yes, we know that the vertical height of that ramp is 4 feet off the ground. And we do know that this angle is 18.4 degrees. So what's given is this angle measure, this side length, and we're asked to find the two missing sides. I'll find A first. So A is adjacent to the given angle, and I know the opposite. So I think opposite over adjacent is tangent. So let me use tangent on 18.4 degrees and set up the fraction 4 over A. Now again, I could flip both sides, reciprocate, put A over 4 and 1 over this, but I think we saw earlier you might as well just go to cross multiplication. So A times tangent of 18.4 degrees equals 4. Let's just divide both sides by tangent of 18.4. I think I'm still in degree mode, so that's good because it's important that I am. Did we have units? Yes, we had feet right here. So the horizontal distance is 12.024 feet. So C's got to be bigger because it's the longer side in that triangle. All right, let's go to another trig ratio. Let's see, maybe we'll use the same one, maybe not. Probably not. All right, so we're going to find C. C is the hypotenuse. We've got the opposite side. Now, of course, I could use this information that I already found, but it's kind of an approximate right here. So I always try and use the given information. So resetting myself, I'm going, okay, this is opposite, and I want hypotenuse. So opposite over hypotenuse over H is that SOHCAHTOA, that SOA sign. Don't forget the degree symbol. Opposite over hypotenuse. Might as well just go ahead and cross multiply. I think I'm just going to go back up here and grab that one, come down to the denominator and change tangent to sine. Yeah, it's longer than the A's value. And that was feet. Okay, we're going to change gears here, but before I come back and before I finish these, I'll come back and finish these, but I want to do one more application problem. Okay, so let me set those notes aside, and we're going to do one more application problem. It's pretty involved. It's actually a problem from the textbook. So if you want to pause the video and find your textbook and then read through problem number 81 on that page, okay, you'll know where we're heading. All right. So here's 81. In traveling across flat land, you notice a mountain directly in front of you. Its angle of elevation to the peak is 3.5 degrees. You drive a little bit more, 13 miles closer to the mountain. Now the angle of elevation is 9 degrees. The closer you get, the more your head has to lift up to look at the top of the mountain. And there's the picture down below. So we're going to recreate this picture on our paper. I didn't have room for this on the printed sheet, so we'll just do this on notebook paper. So we're trying to find the top of the mountain. I'll just put H for the height of the mountain. Okay, so you're in your car, you start here, you get out of your car, you look up 3.5 degrees. You jump in your car, you travel 13 miles closer. I'll put it right here. Now once you're here, your angle of elevation is 9 degrees. You have to look up a little bit more steeply, so I'll put 9 degrees. Probably not to scale, but that's okay. So remember the distance from here to here, you jumped in your car and that's 13. All right, I do not know the length of the hypotenuse. I do not know how much further you have to go to the bottom of the mountain. I'll call that X. Don't think the hypotenuse is going to help me, so I'm not going to label it just yet. I might need to do so later. Okay, so we have this picture here, and we're asked to find the height of the mountain. Okay, boy, that didn't even look like it's a right angle, does it? Let me fix that a bit. There we go. All right, we want to find the height of the mountain. Well, we're looking for a right triangle. I see a couple right triangles, so let's focus on those and see if we can focus on one particular right triangle that's going to help us get H. Well, I see this right triangle right here, this smaller one. Problem is, all I know is that this is 9 degrees and I don't have a missing side. So I can't do what I previously did, set up a trig ratio to help me find h directly. I can set up a trig ratio, but I'm going to have two unknowns. I mean, if I did tangent, it'd be h over x. And that's not going to allow me to find just h. So it's like, okay, what else I got? Well, I see this bigger right triangle right here. Same thing. I look at, okay, I know this is 3.5 degrees. I want to know the opposite side. I don't have any information about the hypotenuse, and I don't have the entire length of this side right here. I've got part of it, but then I still have a little bit that I don't know about. So really, I'm kind of stuck here going, oh, what do I do to get h? Well, this is actually, oh joy, I know you're going to be thrilled, 2 problems in 1. We're actually going to use both these right triangles and set up 2 trig ratios and see if we can use that big mess to help us find h. So our plan is, let's set up 2 trig ratios, one for each of the right triangles. So I guess I'll look at the smaller one first. So I'm going to look at tangent as opposite over adjacent. And so for the small triangle, I'll just label my work here, small triangle, I've got tangent of 9 degrees equals h over x. All right, so if I wanted to solve for h, I would just multiply both sides by x. So I think I'll go ahead and do that. So h equals, the height of that mountain is x times whatever x is times the tangent of 9 degrees. Well, that's not enough for me to find h. So let me look at the large triangle. Okay, well, what trig ratio can I set up on the big pink triangle? Well, I still see the opposite side, and the adjacent side is the sum of these two values right here, 13 and x. So let me do tangent of 3.5 degrees equals h over 13 plus x. Oh, I want to find the height. Let me find the height. I guess I can multiply both sides by 13 plus x. So h is going to equal 13 plus x, make sure I'm putting it in parentheses because that represents a number, times the tangent of 3.5 degrees. And again, I feel like I'm stuck. All right, well, mathematically, what can we do? Well, I see I have 2 expressions, both equal to h. So h is equal to x tangent of 9 degrees, and h is also the same height of the mountain, same mountain, same height. It's also equal to this expression. Let's set these equal to each other, see if we can somehow solve for x. And then once I get x, I'll know I can get the height. So 2 triangles, 2 trig ratios, set them equal. Excuse me. This is a mess. Okay. Mathematically, we're going to persevere here. We want to get x by itself, but right now I've got 13 plus x wrapped up here. So I think I'm going to have to distribute whatever number this is into both 13 and x. So let's distribute. So I'm going to get 13 tangent 3.5 degrees plus x times tangent 3.5 degrees. That's equal to x tangent of 9 degrees. Very weird looking, but we know that this is just a number. I can put this in my calculator and get a number for this. Notice that this term and this term both have a common factor of x. So what I want to do is I want to get both the x terms on one side of the equation. So I think I'm going to subtract this term here to both sides of the equation. You want to get the x's together because we're about to factor out the x. So those will cancel, or yeah, add to 0. So we've got 13 tangent 3.5 degrees equals x times tangent of 9 degrees minus x times tangent of 3.5 degrees. Now, it would be so nice if we could just subtract 9 and 3.5 and say x times tangent of 5.5, but it doesn't work that way, unfortunately. All right, so let me bring down this left-hand side of the equation. Before we change it to a value, let's wait till the end so that we don't lose any of the exactness of our answer. So looking at these two terms, the reason we got them both on the same side of the equation is so that we can factor out that x. So then we've got tangent of 9 degrees minus tangent of 3.5 degrees. And again, that does not equal tangent of 5.5 degrees. All right, to get x by itself, all I'm going to have to do now is divide out this difference, this parenthesis. So x equals, and I'm just going to set up this problem on my calculator, taking advantage of my fraction template. I believe I'm still in degree mode, so I should be good to go. Oh, I better close that parenthesis. Quick inspection, make sure everything looks good. Yep. All right, looks like I'm about 8 miles from the bottom of that mountain. So I'll go ahead and do 5 decimals here because this is not my final answer. My final answer, I might just go to 3, but remember, that's just the additional distance I have to travel to the base of the mountain. But we're trying to find h. So how about if we choose wisely and we come back up here to this h and we just say, let's just multiply our answer, x, that we got by tangent of 9, and that's going to give me the height. So height equals x times tangent of 9 degrees. So h equals, so I already have that on my calculator. I'll just hit times tangent of 9 again. Okay, so the height, and we'll go to 3 decimals. And let's see, I don't think I labeled the units, but I want to say I didn't label them, but in the word problem that we read, this was 13 miles. And that's an additional 8, a little bit more. So the height of the mountain is a little over 1 mile, probably about 6,000 feet. Okay, that took up almost a whole sheet of paper. Wow. Okay, but the takeaway from this is, because of the illustration here, we had 2 right triangles. We needed 2 trig ratios, 2 tangent ratios worked here in this problem. We solved them both for the same variable we were looking to find, h. We set those expressions equal to each other. We did some mathematics on it based upon what's allowed mathematically. We ended up finding x first, but that was okay. It was a simple multiply by another value to get the height of the mountain. All right, that's solving right triangle word problems. Almost done. Okay, let's go back and finish up the other part of these notes on the worksheet. Okay, we changed gears quite a bit here, so that's why I wanted to save these for last. All right, determine whether the statement is true or false. Well, you can certainly use your calculator to assist you in this, but we'll use our calculator to verify what we get solving these without one. All right, it says determine whether the statement is true or false. Is the sine of 60 degrees times the cosecant of that same 60 degrees equal to 1? Well, based on some work we've already done, we know we can change cosecant of 60 degrees to its reciprocal, 1 over sine of 60 degrees. And I can quickly see that those two will divide out, and yes, I do get 1. So this is true because of the reciprocal identities. Okay, now on your calculator, you could verify. Yeah, I'm still in degree mode, right? So sine of 60 degrees times, now I don't have a cosecant key, so what did we do? We changed cosecant, we have the angle, so we just changed that to the fraction 1 over sine of 60 degrees. And it's apparent that these are going to be equal to 1. All right, does secant of 30 degrees equal cosecant of 60 degrees? Well, what I do know without a calculator, I do know that secant of 30 degrees is 1 over cosine of 30 degrees. I'll put a question mark here because that's really what we're trying to figure out. Cosecant would be the same as 1 over sine of 60 degrees. In a previous lesson, I talked about cofunctions. Okay, cosine of 30 degrees is going to be the same answer as the sine of its complement, which is 60 degrees. So these two values will be the same. And to remind ourselves without a calculator, if we looked at 30 degrees on the unit circle, the cosine is square root of 3 over 2 because the y-coordinate's a half. If we travel up to 60 degrees up here and we want the y-coordinate, which is sine, then now we have a half and then we have square root of 3 over 2. So cosine of 30 degrees is the same number as sine of 60. If these two denominators are the same, then this has to be true. Again, you could use your calculator. Find that on your calculator, record that decimal, and then find that on your calculator, see if they match, and it should be true. Okay, how can we tell if this last example is true or false based on some of our background without using a calculator? Well, hopefully you see the squares there, and I see a negative one, not a positive one, but I am thinking about those Pythagorean identities. So let's go back to the Pythagorean identities. Let's see if I still have those. You might have them. Well, I have them right here. Looks a little different than yours. But what I do see is I have cotangent squared of 10 degrees minus cosecant squared of that same 10 degrees. When I look at the different versions, the rearrangements of this Pythagorean identity, I see this last one, I see cosecant squared as first and cotangent squared as second. And that's equal to positive 1. So, I bet I could rearrange here. Remember, I'm trying to determine if this is equal to negative 1. I'm going to take and rearrange and put the negative cosecant squared 10 degrees up front. And that'd be plus cotangent squared 10 degrees. Here, does that equal negative 1? I could factor out the negative here, change that to minus. I could go to my Pythagorean identities and go, okay, now I have exactly what this form is. So all of this can be replaced with a 1, but I do have that negative up front. So this is negative, this is 1 in here. Oops. So yes, that does equal negative 1. So that's true. Again, you could do this on your calculator as well. If you wanted to go to your calculator, not use any of your identities, I'm going to kind of travel upward. Cotangent squared of 10 degrees. We don't have cotangent on our calculator, but we do have tangent. So this term could be rewritten as 1 over tangent squared of 10 degrees. Likewise, cosecant squared could be 1 over sine squared of 10 degrees. If you find this on your calculator, you should get negative 1. It might be a little tricky how you enter the square, so let me just make sure you remember that that would be entered into the calculator as 1 over tangent of 10 degrees, and then that whole quantity would have to be squared. You'd have to pull the square off and put it outside this parenthesis. Likewise, this would be minus 1 over sine of 10 degrees first, and then quantity squared. That's calculator ready right here. This is not calculator ready. Okay, but at the end of the day, it's still going to be true.